One purpose of mathematical modelling is often to try to make valid statements about the situation being modelled. In statistics, the problem is in making valid statements in the face of uncertainty. Take this headline from a 1977 newspaper. 1 in 5 parents dissatisfied with schools. I wonder how they knew that. Did they ask all parents? Well, let's read on. More than 1 parent in 5 are unhappy with the schools attended by their children, according to a survey. So they surveyed some parents. I wonder how many parents they asked. If they only asked 10 parents, say, and 2 of them said they were dissatisfied, that would be 1 in 5. But you'd hardly think that that was the sort of survey from which you could draw the conclusion in the headline there. But you can draw valid statements from surveys, and that's what this program is going to be about. In this survey, how many did they actually ask? Well, the survey questioned 500 parents at random in 5 different London shopping areas. So it's about London schools, and they asked 500 parents. But of course, there are hundreds of thousands of parents in the London area. So on the basis of asking 500, could they draw reasonable sorts of conclusions? Well, people do surveys, and they do ask people to do surveys for them. Barry Hedges works for Social and Community Planning Research.
We use sampling primarily because it's a great deal cheaper than taking a whole count of the population, and it's also a great deal quicker. A whole count of the population, like the national census, costs an enormous number of millions of pounds and takes a very long time to carry out. For most purposes, when people want information, they haven't that sort of money available, and they haven't the time available to wait so long. So they have to use sampling methods, which are very much cheaper and quicker. Our sample is in fact perfectly sufficient to give a very good description of a population. It may seem surprising, but a sample of only a few thousand, or sometimes even only a few hundreds, will in fact give a good description of a population which comprises many millions of people. You can think of the sample, I think, best as perhaps a miniature model of the population. It tends to have the same kind of characteristics as the population, but it won't be an exact replica. That would be asking too much. It will simply be very similar to the population from which it's drawn. But all this is true only if the sample has been correctly selected in a satisfactory way. Now, in order to make a correct selection of a sample, it's essential that everyone in the population has the same chance of being included in the population. This is what we call random sampling. We can't allow some people to have a greater chance of being included than others. Otherwise, we shall have what's called a biased sample, and we shall get the wrong result.
So, suppose we've done what Barry Hedges recommends and taken a sample of 20 parents at random. Here they are, just a tiny sample of 20 parents, but using small numbers enables me to show the theory much easier, and we'll look at larger samples later. And suppose that out of that small sample of 20 parents, 1, 2, 3, 4 were dissatisfied, the ones we've coloured in here. The problem is, what conclusion can we draw from the results of a little limited survey like this? Obviously, the best guess that we can make at the proportion of dissatisfied in the whole population is 1 in 5. But simply jumping to the conclusion that what we get from our sample is what must be in the population is really much too naive. The trouble is that the sampling process introduces chance, and we have to take chance into account in drawing our conclusions. I can show you what I mean by a very simple physical model here. Here are 1,000 bees. And suppose that's the whole population from which we're sampling. And 200 of them are red, and they represent the dissatisfied parents. So that's just 1 in 5. So that's our population. And now I'm going to take a sample from it. put them all into the sampling bottle, and now I arrange to take a sample. And that's easy enough, because this tube will just take a sample of 20. So when I take a sample of 20, out of this, which contains a proportion of 0.2 reds, I might get 4 out of 20 in my sample. You see, in fact, I've got 2, 4, 6, 8 out of 20 in this particular sample. But of course I won't always get 8. If I do the thing again, then this time I did actually get 4, which represents exactly the proportion in here. And just a third attempt. This time I've got 2, 4, 6. So, here is where the nub of the problem is. The sample proportion of reds may or may not reflect accurately the proportion of reds in the whole population from which I'm sampling. And this is where the problem really lies. It will differ in general from here. But by how much will it differ? Well, mathematical modelling is going to help us to answer that problem. But before we get to that, we can do the whole thing experimentally. If we just went on taking samples as I've done here, then we could build up a picture of what sort of samples you might get out of this bottle. Before the programme, we did 100 of those samples, and here are the results on a histogram. You see, here's the sample proportion running from none out of 20 up to 20 out of 20. And the actual proportion in the population, 4 out of 20, came out in my sample as the sample proportion 24 times or so out of 100. But then, so did 3 out of 20. And we got 5 and 6 and 7, and anything from 8 out of 20 down to none out of 20 in these 100 repetitions of this little experiment. So that experiment gives us a way of seeing just how much samples might vary. Samples of the same size taken from the same population. It's a tedious way, though, of discovering that. And this is where our mathematical modelling comes in. We can set up a mathematical model to predict all that. And of course, it has to be a mathematical model involving chance, involving the concept of probability. Now, you met probability in block 4, and there you met the idea of probability and the ways in which you put together probabilities. And those two are the things we need in order to build up this mathematical model. To do it, we think of our sample as being taken one bead at a time. The first bead, then the second, and so on. And this is how it works out. Our first bead can either be red or white. What's the probability of its being a red bead? 200 over 1,000, because 200 of the beads are red. So the probability of a red bead is 0.2. And the probability of getting a white bead, 800 over 1,000, that's 0.8. Now let's think about our second bead. Suppose the first one was red. What's the probability of a second red? There are now only 199 reds left out of 999 beads altogether. That's approximately 200 over 1,000, 0.2. With that approximation, that means the probability of getting 2 red beads in succession is 0.2 times 0.2, that is 0.2 squared. And for the probability that the second bead is white, there are still 800 white beads left out of the 999. Very nearly 800 out of 1,000, which is 0.8. So is the probability that when we take a sample of 2, we get a red bead and a white one, 0.2 times 0.8. Not quite. That's because there's another way of getting one red and one white. That's to get white first time and red second time. The probability that our second choice is red will again be approximately 0.2. So this way of getting one white and one red will also have a probability of 0.8 times 0.2. And the total probability of one white and one red is the sum of the probabilities along each route. 0.2 times 0.8 plus 0.8 times 0.2. That's twice 0.8 times 0.2. Of course, there's one more case to be considered. That's when both the first and second beads are white. The third choice works in the same sort of way. 3 reds, a white and 2 reds, 2 whites and a red, 3 whites. The sequence of probabilities we build up at each stage is called the binomial probability distribution. And we can continue building up the binomial probability distribution until the number of beads in the sample is 20. And that's exactly what we did in order to build up this histogram here. Here again, we've got the sample proportion running from 0 to 1 along the bottom, only this time we've got probabilities up here. So the probability of getting a sample proportion of 0.2 comes out to about 0.24. Remember what probability is? A probability of 0.24 means that if you do a very large number of repetitions of the experiment, then that result will come out 0.24 of the times. But wait a minute, we've already done a long run of experiments. In fact, it was only 100, so that's not perhaps a very long run. But we've got 100 experiments with which to test this model. What we have to do then is to look at these probabilities and compare them with the results that we obtained before. And here they are. And if we put the two together, then we can see that the comparison is not bad. The theoretical probabilities are down below, and the experimental results up above. And the experimental results don't match exactly, but that's because we only took 100 repetitions of the experiment. The more repetitions of the experiment we take, the more we feel that it ought to match up to our theoretical model. But even at this stage, it's quite a good match. Now, what does this theoretical model really tell us? Well, it tells us, first of all, that the sample proportion 0.2 had the highest probability. In other words, the likeliest sample to occur is one with 4 reds out of 20. And that's not very surprising. But actually, it tells us a lot more than that, because it tells us for each other possible sample proportion what the probabilities are. And that is a very valuable piece of information. This is a very powerful model, but unfortunately, what we're saying here is what the probabilities are of getting the particular samples when we know the population proportion. And the problem that we are trying to answer is, having got a particular sample, 4 out of 20, what is the population proportion? Remember, we had a sample of 20 people, 4 of whom were dissatisfied with the schools. And what we were trying to do was to decide what valid inference we could make about the proportion dissatisfied in the whole population. It's as though we had a sampling bottle, and we had taken a sample of 20, and 4 were reds, but this time we didn't know what was in the bottle. And we're trying to decide what's in this bottle on the basis of this sample. Clearly, our obvious guess is that this bottle contains the same proportion of reds as in this sample here, 0.2. But now that we know something about sampling variability, we shouldn't be too ready to jump to that conclusion. So have we really gained anything at all? Well, we have. Suppose this bottle contained 0.3 reds. Then, by going through that binomial calculation over again, we could discover the probabilities of all the possible sample results that you might get, including this one. And this is what you get. The label p equals 0.3 is just a supposition that we're trying out about the proportion of reds in the bottle. If the proportion of reds in the bottle is 0.3, then these are the probabilities of the various sample proportions. And you see that the sample proportion of 0.2 still has quite a high probability, compared, say, with the most likely sample result, which is, of course, a sample proportion of 0.3. But p equals 0.3 is just one possibility. What we'd really like to look at is the probability of getting that particular sample result, 4 out of 20, for any value of p, right from p equals 0 up to p equals 1. And that's what we're going to do. And I want you to look, then, as we look at these histograms for p equals 0 to p equals 1, at the probability of getting the particular sample result, 4 out of 20, a sample proportion of 0.2. We start with p equals 0. As p increases, the histogram moves to the right. But watch the probability of the sample proportion 0.2. Let's see that again. Here are some of those histograms. And we've marked the particular sample proportion from our sample. And as p increases through 0.2, 0.3, and so on, you get a change in those probabilities. Now, I want you to think in these terms. Think of the value of p as defining a particular mathematical model of the contents of that bottle. And for different values of p, you have alternative mathematical models. The consequences of those values of p are these histograms, showing the probabilities. And you see that as p increases, so the probability of getting the sample result that we actually got decreases. And let's stop here at p equals 0.7. You see, because by that time, the probability of getting that sample proportion, 0.2, is so low that you can't represent it in a diagram like this. It's not 0. Logically, you could get that sample proportion from a bottle which contained 0.7 red beads. But it's very, very unlikely, isn't it? And if you think of these as alternative models for what's in the bottle, do you think that p equals 0.7 is a possible proportion of reds in that bottle? Or 0.6? Or 0.5? What about 0.4? The probability is beginning to show here, at least in our diagram. And certainly 0.3 is a possible value because there's quite a high probability of getting 4 out of 20. And of course 0.2 and maybe perhaps 0.1. So when we start thinking in terms of probabilities of getting that particular sample result, we have this sort of feeling about all these alternative models, that there are some values of p that could reasonably have given rise to that particular sample result. And there are other values of p for which the probability of that sample result is so small that we really think that we ought to reject those as possible values of p. And you finish up with a range of values of p that might be the contents of that bottle. Say, in this case, from p equals something below 0.1 to about p equals 0.4. Well, we've illustrated this theory with a very small sample size deliberately, because it's clearer, I think, that way. But even when the sample size is large, the problem is still there. Even, for instance, when we're talking about 500 parents, as we were in our original problem, the problem of sampling variability is still a thing that you have to take into account. And drawing the line between those values of p that you would accept and those that you would reject is one of the important ideas of statistics, which is taken up in the correspondence text. As I said, when you take real surveys, samples are usually much larger than that. That problem is still there, but there are some other problems as well. And to talk about those, here's Barry Hedges again.
It's very important to people like us who carry out surveys. We find that the people who come to us with requests to do surveys have an idea in their minds about how accurately they need the information they want us to collect. So that one of our first jobs is to decide on the size of sample to recommend. And in order to do that, we have to make the kinds of calculation you've been talking about in this program. We have to consider these issues of sampling variability.
So the mathematics that we've done really does underlie that. But from your point of view, it's determining the sample size.
Yes, it does indeed determine the sample size, which is one of the main determinants of the cost of the survey.
Now then, we've talked about sample sizes, but you talked earlier about bias.
Yes.
Say a bit more about that.
The bias is a very important idea, but however large your sample, it won't be a good representation of the population if it's biased. I said earlier that you will get a bias if you select your sample badly. That's to say, if you don't give everyone in the population the same chance of being included. And that is a very common form of bias in surveys that aren't carried out too well. But there are other kinds of bias. You can get a bias if the people you approach don't all agree to cooperate in the survey. There are always some who won't take part, and if their characteristics aren't the same as those of the people who do take part, you will get a bias there. Fortunately for us, the evidence is that the people who don't take part in surveys aren't so very different from those who do.
Thank you very much, Barry.